in the first part of this lecture today, we talked about estimating parameters when the data set is complete. And as we saw, it's pretty well behaved. You can effectively compute these estimates in closed form, and they have all kind of interesting properties. In particular, we've seen that they're unique, asymptotically normal. They maximize the property of the data. And as I mentioned, they can be easily computed by performing a single pass on the data set. So we've started by defining these estimates as the ones we obtained from the empirical distribution, but then we have proven, we didn't prove, we stated the further properties, and the proofs are in your book. As I said, typically this is done the other way around. You go ahead and say, I want actually maximum likelihood estimates. That's what you start with, and you arrive at the ones we discussed. And people have justified maximum likelihood estimates based on a number of considerations. And these estimates have these properties not just for Bayesian networks, but for a larger class of models. So that's what we're going to do next. Now we're going to look at estimating parameters under incomplete data, and the goal would be to just try to optimize likelihood or maximize likelihood. So first of all, let's look at a concrete example and get to say a little bit about this notion of incompleteness. This is a simple example. We're going to use two variables only, C and T. So we have a condition that a patient may have, and then we have a test that bears on that. So C goes to T, and here's the CPT for the root variable C, and here's basically the CPT for the test given the condition, right? And just an observation here that according to this model, the probability of a positive test versus negative test is basically equal. Now, let's look at three different data sets for this particular example. And let's call them D1, D2, and D3. So look at them for a little bit, and we'll say a couple of words about each one of them because they exhibit different types of incompleteness as far as the data is concerned. So if you look at this guy, for example, look what's going on here. In every row of the data set, the value of the condition is unknown, right? And T is always known. When we have the situation, the variable C is said to be hidden or latent, right? So it's always missing. And if you look at the second one, no, C is always known, actually in this case, so it's observed. This is an observed variable. And T sometimes is known, sometimes it's not. So now we've seen C being hidden, C being observed, always observed. And then the third type is you see both types, right? So we don't have hidden variables. We don't have observed variables. C sometimes has values, sometimes does not, and T and so on. Again, some of these distinctions will become relevant later. Now, first observation about estimating parameters from incomplete data. For this particular example, if you go ahead and do the math and say my goal is to optimize, find the parameter estimates that optimize likelihood, and we have the equation for likelihood, you do the derivatives, and it's all in your book, you find that you can characterize ML estimates by this equation. So as long as you have estimates that satisfy this, they will be maximum likelihood estimates, and there's no unique solution for this guy. For example, the true parameters, that is the ones in the original network we started with, from which we were generating the data, does satisfy this equation, but you can satisfy it in many other ways, as you can see here. So if you choose this parameter this way, that parameter this way, then you're good regardless of what this is. You're still going to get this condition, and you're still going to get maximum likelihood estimates. All right, so they're not unique. Maximum likelihood estimates are not unique when the data is incomplete. Okay. I want to mention one more phenomena regarding missing data before we talk about the main method for estimating parameters in this case. And I'll allude to it. We'll see. There is the solution to this also in your book, or some interesting observations. But let's at least just do this. Look what's going on here. I know whether the person has a condition or not in every case, but the test results are sometimes missing, right? There's this question about why is the data missing? Okay, consider the following two scenarios. Scenario one says people who do not suffer from the condition tend not to take the test in the first place. That is, the data is missing because the test was not performed to start with, right? Now look at the second case. People who test negative tend not to report the result. Big difference. The test is performed, but its value is not recorded. Now, what's the difference? The difference in the second case, a missing value is somewhat indicative of what the true value is, right? That is information. The method that we will discuss, which is the classical method, doesn't get into this business. In fact, if you have this kind of a situation, what I'm going to be telling you now will not be directly the right way, right? You need to do something about the situation. Sometimes people say, you hear that a lot. They say, we're going to assume that data is missing at random. That has an intuitive meaning, but it also has a technical meaning. The intuitive meaning is, I cannot infer anything from the fact that something is missing, like in case 2, right? So then the method I'm talking to about is good. It's not missing anything. It does have a technical meaning, which technical definition, which ends up being basically the same. So what we're going to be doing next is talking about the method for estimating parameters under incomplete data when the data is missing at random. So you won't learn something from the fact that something is missing. And the handling missing data is actually fun. You can use the method that I'm going to tell you about to handle the situation, but then you have to augment your model with what we call the data missing mechanism. You have to talk about the causality of missingness by adding more variables and so on. It's all right. So estimating parameters from incomplete data. We'll talk about two methods, one in detail and the other we'll just sketch. And you'll see why will be enough with a very quick sketch of the second method. Both of them are what we call local search, in a sense. They start with some initial estimates and then iteratively improve them until some stopping condition is met, right? So the nature is this. Here's a structure, here's data. I initialize my parameters, so I already have estimates to start with, and then I start making iterations, right? And every iteration I have new estimates until I stop. They're both more expensive than doing complete data, and neither is guaranteed really to find maximum likelihood estimates in the sense of global optimization, right? They are best effort methods. They do come with some guarantees. The first one, in particular EM, you'll see it gives you some interesting guarantees though, but there is no guarantee that they will find the optimal or an optimal estimate. Okay. Now, this is the first method we're going to talk mostly about is expectation maximization, or EM. It is actually the way we're going to introduce it or motivate it by an extension of the method we did for complete data. You're going to see a very intuitive extension, just to give us the spirit of what's happening. But then when we go to the closed forms or the equations for it, they will be more direct, right? So the explanation will be hairier but intuitive. But then finally the equations will be very simple. The algorithm is simple to implement, and you'll see, for example, how it will feed off computing marginals over families, something that we already mentioned multiple times, that that estimation algorithms require marginals over families. You're going to see this next. Okay, so let's illustrate this EM algorithm using this concrete example. We have this structure, right? 4 variables, A, B, C, D. And here's our data set. The data set only has 5 examples. By the way, a row is also called an example. An example, a unit, or observation. Probably example is more common. And you can see the missing data in this case, right? Our goal is to find maximum likelihood estimates for the given data set. And the way this algorithm works is you initially guess your parameters. And that's what we've done here. So we initialized our parameters to these. And you can see the notation here, theta, the subscript is 0. That is the parameters at iteration 0, right? So let's say random for now. They don't look random, but let's say random. Okay, now what do we have? Now we have a model, and we have a distribution, correct? Okay, now look what's going to happen. And the notation is this. This is the distribution PR of theta 0, correct? Okay, look what's going to happen. First is the quality of these parameter estimates at iteration 0, just to be concrete and illustrate the main point about this method. Here's the definition, right? You just go iterate over all 5 examples in the data set. You compute the probability of each with respect to the current parameters. You just do this, you get this number. That's the score. That's the quality of our initial estimates. And the one thing you have to observe here now is the following. Look at the components of this guy. Each one of these is what? Is the probability of a partial variable instantiation. You need inference algorithms to evaluate the score, by the way, right? It's not trivial to get this number. You have to do inference. Effectively, you have to walk through your data set and compute the probability of each example. If this was a complete data set, this would have been easy, right? Because in each one of these terms would be the probability of full variable instantiation, which we know we can compute efficiently, but not in this particular case. Okay, now let's go back to the example. We started by some initial estimates. Now we have a distribution. Here's my data set. It is not complete. The essence of this method is the following. It is not complete, right? Look at the first guy. How many missing values? 2. Let's say this is a patient. I know 2 things about this patient. I don't know A and D. Assuming these variables are all binary, there are 4 possible completions of this particular example, correct? I don't know which one is the reality, correct? The main insight of this method is, now that I have a distribution at iteration 0, I can use it to do what? To talk about the probability of each one of these completions. Look at it here in more detail. Don't be scared. This is very friendly. What we did here is we fleshed out the data set. Here's the first example, D1. I know B and C, I don't know A and D, correct? There are 4 different ways to complete A and D. Here are the 4 different completions. You guys see that? What is shown on the side? The probability of that completion. What is the probability that it is indeed this guy, A1, B1, C2, D1? What is that probability? It's 0.111. The key is this probability according to what? According to my initial estimate, theta 0. Good? Now, you do that for the second completion, for the third completion, and so on. And then you go to the second data set. And the second data set is also missing 2 variables. That's also 4 completions. You can see the probabilities of each. And then the third example is missing only 1 variable. That's 2 completions. Here's their probabilities. Fourth example, also missing 1 variable, 2 completions. Fifth example is missing 2, 4 completions. Here they are. You guys see what's going on here? Now, what can I get from this? An empirical distribution. That's the empirical distribution based on this. When you have an incomplete data set, there is no notion of an empirical distribution. But if you complete it, then you can start talking about an empirical distribution. But now what do we call that empirical distribution? We call it the expected empirical distribution. And this guy is a function of what? Of 2 things. This distribution is a function of 2 things, right? The data set, D, and the parameterization, theta sub 0. To get this guy, it's not enough to have a data set. You need a data set and a distribution to do the completions, to take an incomplete data set and turn it into a complete one. You guys see what's going on? EM, of course, doesn't do it like this mechanically. I'll show you at the end how it does it mechanically. It's a shortcut. But conceptually, what it's doing is this. Guesses initially a set of parameters, theta sub 0. Now I have a distribution. I have my incomplete data set. It uses that distribution to complete the data set. What does it get? An empirical distribution. And then what does it do? It uses this to compute what? The estimates, theta 1. Just like we did with complete data. Based on this guy. What's going to happen next? Now that I have theta 1, what do? I repeat the process. Now that I have theta 1, I take it and use it to complete the data set again and get another empirical distribution, and I use that to get theta 2. Now you're probably have two questions now. When do we stop? And why is this a good idea? Correct? We'll see interesting answers for both of these. But let's just, with the equations, this shows conceptually what's going on. If there's simple, nice equations. They're simple when you write them. They're hard to evaluate. Equations for EM. Let's just get there first. There is two equations. This, which explains what we just said, and the more direct one. This talks about this notion of an expected empirical distribution. The one that depends both on the data set and whatever set of parameters you have at iterations k. And how do you use it to compute the probability of some alpha? Alpha is some arbitrary event. What am I doing here? I am iterating over every example d sub I. Now that d sub I is not a complete example. Some variables are not known. Ci is the completion of that guy. So Ci is an instantiation of the variables that are missing in example I. So this sum is, now that you have di and ci, now I have a complete example, right? So d and c together fix the value of every variable in example I. And this is the probability of the completion. According to this method that we just did, this would be the estimates at iteration 1. There's three questions here we need to finish this. One, I have to show you the final equations that this guy used, the thing that you would implement. Second, why is this a good idea? And third, when do we stop? Earlier, we computed the likelihood of theta 0. Right? Now we're going to compute the likelihood of theta 1. Same story. You just go over the examples. You compute the probability of each example. You take their product. You get this. This is actually greater than the likelihood of theta 0. That is not completely accidental. In fact, this method, the new likelihood cannot be smaller than the previous one. You get a guarantee that it is either better or the same. So when it says, why do we iterate? Because you cannot worsen things. Here's the guarantee that the log likelihood at iteration k plus 1 is greater than or equal at the previous iteration. And here are the equations of EM. So I showed you one equation that tried to notate what we said intuitively about that table of completion and so on. And again, you can ignore it. This is the guy, the final guy. This is what you need to remember or visualize, right? This is the EM estimate of the parameter theta x given u. Iteration k based on the estimates at k. Look what it's doing. Okay, I want you to look at this because that tells you a lot about the computational complexity of this algorithm. At the top, what's happening? I'm iterating over every example in the data set. What am I doing? I am viewing that example as evidence. I'm conditioning on it. And then computing the probability over the family. Try to visualize it like this. Here's your data set. It has 1,000 examples in it. The algorithm will go down, example by example. Take it, assert it as evidence on the network, compute marginal over the family. And then go to the next guy and the next guy next. You need to do one of these iterations to what? To produce the next estimates. You have to do a pass over the data set and compute family marginals under every example treated as evidence, to do one iteration of this guy. See now the relevance of inference here, right? This is inference. If you get these guys, you can just get these guys from them as a side effect, right? Because if you have this, you just sum over x, you get that guy, right? So you see now in the code, this is what's computed in every pass, and then you get these as a side effect. But you guys see this? That's EM. And that gives you a sense of how much work it is actually doing. Okay, let's look at the pseudocode and make a couple of observations. Here's the network structure. I'm starting with some initial parameters set as 0, and here's the data set, right? That's how we're starting. And remember, families, we're iterating, starting k equals 0. Okay, line 2, what does it say? While the current parameters are not the same as the previous ones, do the following, right? This is not a very realistic test. If you do this, you'll probably never stop. This test is different in practice. Okay, so look what's happening. These are the counters. You initialize these counters over families. And then what do? You iterate over the data set from I equals 1 to n. And then for each family, you do this. If you're using a joint tree algorithm, you get all of these at once, correct? Joint tree algorithm, you condition on the example I, you run the joint tree algorithm, you get all marginal at once. You get this also from circuits. If you have a circuit, same thing, but you have to do 2 passes, up and down, for every particular example, and you get all of the marginals over, and that's these guys, and then eventually you sum over x, and that's one iteration. That's basically the EM algorithm. What people do for stopping, they look at the distance, actually, some kind of there's different ways of measuring the distance between one set of parameters and another set, and if they're close enough, you stop. Sometimes they actually do the compute the likelihood and also do tests on likelihoods and so on. So you will need to have a looser test or a weaker test for convergence. I will do the following couple of slides for completion, to have a complete coverage of EM, and in particular explain the name. Why is it called expectation maximization? Depending on your taste and interest, the next few slides may look like they're too much. If they're too much, ignore them. If they're intriguing, you can look more in the book about them and their derivations. They really take you to one deeper level about what's going on with EM. The analogy here is with the complete data case. So if you look at the complete data case, we had the likelihood, correct? Log likelihood. And we said we want to optimize that. And then we found that this empirical probability does that, correct? It's just a one-shot thing. I want this guy optimized. Here are the parameters that optimize that guy, okay? And in the case here, it's a little bit more involved because I don't have a complete data set. I have a completed data set. So here we talk about the expected log likelihood as opposed to log likelihood. And this is the equation. Expected log likelihood, now not just with respect to data, with respect to some particular parameterization, theta k. And this is the definition. It's similar to the previous guy, except that you have the notion of a completion and the probability of a completion, really. I mean, you can parse it. And then you can show that if you actually compute the empirical probabilities, but again, according to the expected empirical distribution, these guys optimize that guy. So this comes some kind of a parallel between the two cases, and the other case falls as a special case of that. And in each iteration, what EM is doing is optimizing that guy, the expected log likelihood. Again, you can look at the math in your book on this. Otherwise, you can just leave this alone if it's too much. And then you can see also why do you get that guarantee that in every iteration things cannot get worse? Because if you're actually optimizing the expected log likelihood, then basically you can do worse. That's where the why this guarantee is coming from. It's because you're doing this, right? So that's, even, as I said, digging even one level deeper into what's going on. And here's a couple of other observations about EM. EM is capable of converging to every local maxima of the log likelihood. Local maxima, right? And the fixed points of EM are precisely the stationary points of the log likelihood. The EM algorithm is known to converge very slowly if the fraction is quite large, and . So you get local maximas from this, not global. So what do people do in practice? First of all, you can imagine this is going to be sensitive to what? When you run this algorithm, it's going to be sensitive to starting point, right? Where you end up being depends on where you started. So what people do is they run it multiple times. And every time they seed it differently. So when you find results in the literature, they will say we ran EM 10 times, seeded it randomly, ... Okay? And that's pretty common with these kind of methods where you will do that. EM is very important. It's a bread and butter for a lot of work. It's the method of choice in this case for incomplete data. I'll tell you about another method in one slide, actually. Gradient ascent. You can think of the likelihood. It's a function of the parameters. The data is fixed. And then anytime you go put parameters in the network, you get a different likelihood. So you can go and define the function, the likelihood, which is a function of many variables, these variables being the parameter estimates. And since you're trying to optimize likelihood, it's just a classical optimization of a function of many variables. And so you talk about this function, f. The v's are the parameters. And I'm trying to choose the values of the v's so that I can maximize the value of that guy. Classical ways to get the gradient and do gradient ascent. And as you know, when you do that, one of the issues is how do I do the increments as I'm following the gradient. So people call that the learning rate. You have to deal with that. But the interesting thing about this, imagine if you implemented this algorithm. It's also going to be iterative. You're going to guess something to start with. You're going to compute the gradient and do what? Step. And then compute the gradient again, another step, correct? So at this high level, it's the same. Now you're going to say, but wait a minute. So the only thing that's missing in implementing this method is what? How do I compute the gradient? And then you may say, wait a minute, can I do better than EM? Like, is computing the gradient easier than getting marginals over families, which is the computational ingredients of EM, right? Not really. If you look at the gradient equation is in your book. And it ends up being the same amount of computation. It is actually based on the marginals over families. It ends up being pretty much the same. You have to walk through the data set, and for each example in the data set, you have to condition on it and compute the marginal over the families, and it's those marginals over the families that define the gradient. I'm not even showing the equation here, but you can check it in your textbook. We good? Okay, so going with our tradition of shortening lectures a little bit, we'll stop at this point, and next time we will talk about learning the structure of Bayesian networks from data. So I'll see you on Tuesday.